Okay, so we are going to start with the second lecture. Uh, what we have learned in the first lecture, the definitions and the solution properties, we are going to now see that how we can apply those concepts, those quantitative information when we have to begin with the synthesis and properties of the nanomaterials. Okay, so here it is micro heterogeneous aqueous for nanomaterials. What is the meaning of this? Yeah, as I told you in the previous lecture, that the definition of the solution is where we could see the complete miscibility between solute and the solvent. Solute could be in the solid state or in the liquid state or the gaseous state. That is not any kind of the part of the definition. The solute could be any component which is in much smaller amount in comparison to the solvent. What is micro heterogeneous? Heterogeneous we know, homogeneous and heterogeneous. Solutions, clear solutions are homogeneous no matter which kind of solute you are going to add in a solvent. Heterogeneous is where the miscibility is not appropriate. That kind of a mixture is heterogeneous. For example, the simple example is oil in water. So oil in water, there is practically no miscibility, and we call it's a heterogeneous phase when if there are two components, so they are not miscible. What is the meaning of micro heterogeneous? The micro heterogeneous is it means that we are talking about we are dealing with a term or the solute in terms of the dimension. Here I would say that we are dealing with the solute in terms of particles. Now when we introduce the definition of a particle, so what is the dimension of the particle? Nature has provided us the eyesight or the naked eye can focus on certain object, on the object of a certain dimension. For example, that nature provides us the ability to see a single hair. But if you reduce the thickness of the hair, we won't be able to see that. If you pick that hair, which is much thinner than the normal hair, and put it in pure water, you won't be able to pinpoint that, right? So micro means I'm typically saying that I'm talking about the scale. So that is in terms of 10 to the power minus 6 of a meter. That is a micro. Nano 10 to the power minus 9. So in this way, here we will be talking about the solution that is being prepared by a heterogeneous, which is in fact a heterogeneous solution, but that heterogeneous solution looks to be homogeneous. So therefore, the conventional definition, now the next question is, can we apply the conventional definition to this kind of heterogeneous solution? Yes, obviously, you won't see this in the textbooks. But yes, we can apply it as long as we see a solution clear with the naked eye, and the solution chemistry definition says that is a homogeneous solution, right? Now in that homogeneous solution, and the solution where the solute is in the suspended state, which is entirely not miscible with the solvent phase, but it's entirely suspended state. So that is meaning of micro heterogeneous phase or the micro heterogeneous solution. Okay, so I begin with the definition of nanoscience. You already know that the dimensions of the particle when they reside between 1 to 100 nanometer. Most of the time, nanotechnology deals with such kind of objects. So then, the technology or the devices or the procedure or the protocol where we are using them, so we call them that it is a nanoscience. Nanotechnology where we use these small object in the form of the part and to develop any kind of what we call the device or the methodology. So that is nanotechnology. Nanochemistry, because in order to produce these small components, obviously you have to start from the materials which are being used. They may be made up of copper, silver, platinum, or any kind of oxide. So then that is the chemistry involved in order to produce those objects by using these kind of materials is known as the nanochemistry. Now, when the size of the object is in micrometers, you see mu stands for micro, 10 to the power minus 6. When the size is in micrometer, so your naked eye has the ability to see this. And obviously, as I told you, the hair, the thickness of the hair is from 10 to 20 microns. But the problem is, if you have the blood sample, whole blood sample, the size of the blood cell is from 4 to 10 or 4 to 8 microns. You won't be able to pinpoint the single blood cell. It means that naked eye is unable to pinpoint or to focus on the single blood cell. So therefore, as far as our natural ability to see the objects is concerned, so that is the scale beyond in 10 micron or maybe 20 micron. But nanotechnology deals with a scale. Rarely it goes to a micron. Most of the nanoparticles which are being used for environmental applications or for other kind of device formation, you may say, so they have the dimensions, at least one dimension, because you have x-axis, y-axis, or three-dimension. After the three-dimension, at least your one dimension must be in nanoscale. So suppose if we have a nano particle which is in the form of a filament or a kind of a ribbon, it means that out of the three dimensions, at least one must be in nano dimension. Either the thickness should be less than 1 micron, or the width should be 1 micron. Length cannot be less than 1 micron, so that is the definition of a ribbon. So that is the meaning of nanotechnology. And how we can use the different synthetic protocols of chemistry to apply in order to synthesize nanomaterials. Practically, we have two predominant approaches. One is top-down and bottom-up. What is the meaning of top-down? Top-down means we have a large amount of material whose nanoparticles we want to make, right? And we will grind it with something. We will use the mechanical force in order to convert the bigger size into a smaller size. That is a very crude way of producing nanomaterials. Usually, the top-down approach, usually it is not fruitful in producing the nanomaterials of the same dimensions and the size. So therefore, it is not that popular. But the bottom-up approach is much popular, where we are using atoms. We control the synthesis of atom. We allow the atoms to fuse with one another, and we control their crystallization, nucleation, so that a particular shape and size of the object is being created. Thank you. So that is the way we allow the atoms to produce the nano object. That is, atoms, I mean to say that if we are dealing with the transition metal nanoparticle, gold, silver, platinum, or maybe the oxides, so then we are using atoms to produce the nanomaterials. But if we have the soft nanomaterials, soft nanoparticle means the particles of the polymers or any kind of carbohydrate, or we want to use the particles of proteins, I mean to say the bigger molecules, then we can use the molecules which are already dissolved in water. We convert them, we control their aggregation, and we convert into the nanoparticles. And so therefore, proteins molecule-wise nanocrystals. So eventually we produce the nanoparticles. So keep in your mind that there is a common term which we use, nanoparticle. When we say, if somebody say that, can we apply the term nanoparticle to any kind of nanoparticle, or it is restricted to gold, silver, platinum nanoparticle, or any kind of oxide nanoparticle? What if we have the uh, 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 aggregated entities of the soft materials like polymer? Should that be termed as the nanoparticle? Yes, absolutely. The nanoparticle is a common term that can be used for the particle which are being synthesized from the atoms of the transition transition elements, or we may use any kind of molecules. So therefore, soft or hard. We then differentiate the nanoparticle in the category of soft and hard. Half hard nanoparticles are crystalline. Protein or the carbohydrates, the polymer nanoparticles never be crystalline. So therefore, they are included in the soft nanoparticle category. How we can produce them? It is in fact the synthesis is in fact the branch of chemistry. So therefore, any researchers who is working in the nanotechnology, he or she should have some sort of information of the synthesis process of the chemical reaction, that which kind of reaction he or she has to pick in order to synthesize the nanomaterial. So the basic chemistry is very important. The knowledge of the basic chemistry is very, very important. So here we begin with, I'm not showing the entire solution. Now you know the definition of the entire solution, right? So here I am talking about only the solute. You may say that I have intentionally excluded the solvent element, solvent part, that is the water molecule, and only trying to put my attention on the reaction which will help you to understand how to synthesize atom. There are two ways. Here is the reduction. You will be adding the electron. This plus refers to the addition, not the charge. When you add the electron to the cation, you will produce the atom. You remove the electron from the anion, you will produce the atom. Usually the first one is the most popular because you have plenty of common reducing agents. You can use them, right, to provide the electron. So therefore you can easily produce a new neutral atom. So I mean to say that if you are choosing to have the gold salt, gold chloride is the most convenient salt we can use to produce a gold nanoparticle. So gold is in oxidation state 3. If you provide 3 electrons by using any kind of reducing agent, this is a very strong reducing agent, sodium borohydride, but you can use the sodium citrate or ascorbic acid, or there are other weak reducing agents, so they will also serve the purpose. But the only difference is you have to be very careful that how you have to control the atoms in solution, because now the thing is that when the atoms are produced in the solution, there is no way to monitor them immediately because they are happening at a very rapid scale. Right? So therefore, at that point you have to control the crystallization to achieve the particle size for the nanoparticle. But how you can control that? A reducing agent can help you. If you are choosing a strong reducing agent, it will instantaneously convert all cations. If you are choosing cations, they will reducing agent will convert all cations into atom just as soon as you are going to add them. But if you are going to add the weak reducing agent is time dependent. So it will take time, right? But there is difference. When all atoms are produced at once, the nucleation will instantaneously begin among the all atoms. But if you are choosing slowly weak reducing agent, the nucleation is going to be diverted to the different route. So therefore you have to be careful in which route you have to follow, right? So usually what we do when we have to produce the nanoparticles of small dimensions, right, and then we choose the strong reducing agent, but when we have to control the size and to produce a certain shape of the nanoparticle, then we choose the weak reducing agent. So here we add the reducing agent and we produce the gold nanoparticle. Now you see that we have the gold nanoparticle. Here, the fundamental definition of the dissolution of solute in solvent comes. You see now, this solution is clear and red in color. What is the meaning of clear? Clear means when you can see through the solution. That is the meaning of the clear solution, right? So turbid is when you cannot see through the solution. So when you see through the solution, it means that you have a homogeneous suspension, stable suspension. Stable will be, how much stable it is will decide on the shelf life. How long, if you keep it on for a longer period of time, eventually nanoparticle will settle down and again you will have the transparent solution. If you have to use this kind of a solution for some kind of application, right, so then you have to have the stable solutions, stable nanoparticle. It means that the shelf life should be for the extended period of time. Somebody asks you that how we can determine the stability of a gold nanoparticle solution. You will be saying that the stability of the gold nanoparticle solution depends on the nature of the stabilizer which you are going to use over here. You see, this is the stabilizer. Now, you have already read about the term colloidal. So now this is colloidal solution. The microheterogeneous solution is in fact the colloidal solution. Colloidal solution where the particle dimension is between 1 nanometer to all the way up to 1000 nanometer, and if that is going to produce a homogeneous solution, we call a solution the colloidal solution. But there is a condition. You cannot prepare a colloidal solution without adding a stabilizer, because if you do not add the stabilizer, the reaction is going to produce, that is fine. You will see the red color. But the particle which you are going to produce, they are not that stable which you are expecting, right? So therefore, the stability of the colloids is very, very important in order to use the colloid for any kind of application. You have to keep in your mind that application part may consume time for 1 day, 1 week. I mean to say, suppose you have to use the gold nanoparticle for a particular kind of application. And usually, as soon as you have prepared the gold nanoparticle, you are not going to instantaneously use for that application. You may need some pause, some time interval. So therefore, that time interval could be few hours, or it could be few weeks. It means that your gold nanoparticle solution must be stable for that longer period of time, so that you can easily use it for a particular kind of application in order to see the reversibility. You got my point? You should have quantitatively you must see that that reproducibility you are going to achieve, that could only be achieved if your colloidal solution, gold nanoparticle solution, is stable enough. Okay, now how we can achieve the stability of a colloid? Here, this slide I have a typically, How we can achieve the stability of a colloid? The best way to achieve the stability of a colloid is to produce the electrical double layer on the surface of the particle. You might have heard about the electrical double layer in electrochemistry. Electrical double layer is being established on the surface of a particle when it's suspended in a liquid medium. That could be, usually it is aqueous phase. That makes more sense in comparison to the non-aqueous or polar solvents. Now, next question is, if we suppose add sodium chloride, would that be fine enough to create the stability over here, right? The stabilizing agent or the capping agent. Capping or the stabilizing, capping means that we are producing a blanket of a layer around the surface of the particle, so that that blanket of the molecule, so that can interact with the dipolar water medium, and that would produce electrical double layer to provide the colloidal stability. Sodium chloride is not a stabilizer. In fact, sodium chloride, no doubt it is going to produce electrical double layer, but that electrical double layer is not having predominantly negative or predominantly positive charge, because the sodium ions, if the sodium ions are going to absorb on the surface, chloride ions are the counter ions, they are going to balance that charge. So therefore, sodium chloride is in fact inducing the aggregation of the nanoparticle, hence we cannot use the sodium chloride. But on the other hand, we can use a surfactant. We can use a surfactant. Now, what is the meaning of a surfactant? Surfactant is the word that refers to the molecule which is active at the interface. So which is interface? It is air and water. So here you know the water, here it is air. So the surfactant is, now surfactant is a molecule who has the dual ability to interact with the polar and the non-polar. It's surface active, this is the polar part and this is the non-polar part, right? So you can see from the molecule structure of a surface active molecule, right, the non-polar part will not be, we will not be able to introduce into the aqueous phase. So therefore you have only one way of the placement in the aqueous phase, that is only at the interface where the polar part is going to be immersed in the water phase and non-polar is going to be in the air. So this kind of ability a molecule is possessing to be active at the interface, that is known as surfactant. And the same thing is happening over here. This is the interface, it's the solid phase, it's the aqueous phase over here. So the polar part, because it's a transition metal, this is a free electron cloud, so the polar part positively charged head group, so that is interactive to the free electrons cloud, and hence there are electrostatic interaction. The non-polar tail cannot stay in the aqueous phase, so therefore there is another layer of the molecule that allows the non-polar interaction, and the polar head group remains suspended in the water molecule to interact with the water molecule through electrostatic interaction. This is a bilayer. Then this is a bilayer. Now this bilayer, you see now, this bilayer is charged. You see over here, this is the head group. So there are counter ions for this one is, because every surfactant, if you say that, if I say that this is positively charged surfactant, in fact all surfactants, they can be categorized in ionic, non-ionic or pseudo-ionic category, and most of the time for the stabilization we use the ionic surfactants. So if this is a cationic surfactant, so there must be chloride, bromide or any other anion that can be used as a counter ion. But the difference is here, the charge which you are going to see over here, that is much different the way the sodium ion is going to be absorbed over there, right? So therefore the absorption of the counter ion is not that effective here on the bilayer as much over there. So the stability, a bilayer, which whatsoever the stability it is going to provide you, that is much more effective in comparison to the stabilizing ability that is being provided by the sodium ions. So this stability now, the bilayer stability helps to provide the colloidal stability and helps in the stabilization of the nanoparticle. Now it all depends on the nature of the surfactant you are going to choose for the stabilization. That will determine the shelf life of the nanoparticle solution. If the surfactant is a weak surfactant, weak means that, what is a weaker surfactant? Weaker surfactant is the polar part is predominantly more polar, but the non-polar part is less non-polar. So this part is predominantly polar, this part is less predominantly non-polar, that's the weaker surfactant. But if this is much more non-polar in comparison to polarity, this molecule has no other possibility except to arrange at the interface. So therefore you have to choose that which molecule, surface active molecule you are choosing for the surface activity. Sometimes surfactant can also lead to the aggregation. I mean to say that it is all experience. So I cannot deliver a blanket statement where I can say that no, this surfactant will give you this much stability, that surfactant is going to provide much higher facility. Usually the double tail surfactants, they are much better stabilizer in comparison to the single tail conventional surfactant. Single tail conventional surfactant, sodium dodisulfate is the most common conventional surfactant you might have seen in your many lab experiments. Okay, so apart from this stability, you can also choose, if somebody asks you that this is the only kind of a molecule, how can we prove this, that there is really a bilayer? So now you see in advanced research, everybody as a researcher, suppose if you ask me, though for quantitative analysis you need the math, but I always prefer to use the technique of the protocols which require less kind of methodology, theoretical theories, but more direct evidence. So imaging techniques, that's why in material science, in material chemistry, imaging techniques are very, very important, right? Imaging techniques can give you direct evidence of the bilayer formation. Suppose if I don't have this image, it is very, very difficult for me to prove that there is indeed a bilayer, right? So I may use a different kind of theoretical methodology or theories based on the surface science or surface chemistry. But eventually, I still may not be able to convince 100% that there is really a bilayer formation. But if I have a real image, I can really prove that the length of, the thickness of this bilayer is 4 nanometer. It means that you will calculate the length of the tail this and length of the tail this, and obviously the size, add them, and you will see. And if it is close to this, this is the transmission electron microscope. So I have to say few words regarding to the imaging technique. Whenever you have to read or see or to understand the transmission electron microscopic image, the first thing is it is known as a TEM, transmission electron microscope. There is one in GNDU that is not working. We don't have a none here in NIT. There is one in Punjab University that is working, and I think there is one in Punjab Agriculture University, PAU. So it is not a camera photo. You have, everybody is having the cell phone. When you take the photograph, you are not having the scale. And from the photograph, by taking with your cell phone, you cannot make out that what is the height of a person whose photograph you are taking, what is the width of a person, you cannot make out because there is no scale bar. But in material science, when you are going to take the image through the transmission electron microscope, the best way to read the image is first attention, you must focus your attention on the scale bar. So this much length refers to 20 nanometer. It means by concentrating on this much length, you can just check the diameter of the particle. So you see that the diameter of the particle may be 25 to 30 nanometer, right? And you can precisely, on the basis of the scale, you can precisely calculate the length of the bilayer, the width of the bilayer, and then you can quantify that whatsoever the model you are predicting, you are proposing, so whether that can be proved with the imaging analysis. So it is not only just one particle you need to see. So all the particles should have this kind of a shell around the surface to prove that there is indeed a bilayer formation. You got my point? You don't have to pick just one. It means all of the particles should be alive and they should have the same image. Okay, so this is the way we explain, and there is another way. If you are, as I told you, that it's not only the surfactants which we are going to use for the colloidal stabilization, you can also use the polymer. So our basically the requirement is, if somebody asks you that what is the concluding requirement in just one statement, what kind of stabilizer should be? You have to say stabilizer should be, the first aspect is surface active. If that stabilizer is not surface active, not all molecules are surface active, only surfactants are surface active, then what is the other condition, other requirement? You can say that if the molecule is not surface active, then the molecule must be amphiphilic. Must be amphiphilic. What is the meaning of amphiphilic? The molecule that is possessing the functional group which can interact with the non-polar part, non-polar entity, and the functional group which can interact with the polar entity. That is an amphiphilic molecule. So the polymers are amphiphilic. So you have to choose a amphiphilic molecule. So all water polymer, so water soluble polymer, so they are amphiphilic molecule. So any you can say the polymeric alcohols you choose, and polymeric alcohols, so they have plenty of hydroxyl group. They interact with the water molecule, but you will never see the polymeric alcohol is going to be absorbed at the interface, because the electrostatic interactions are so intense with the water molecule through the hydroxyl group that they will keep entire polymer in the aqueous bulk rather than at the interface. But that polymer certainly can absorb on the surface of the nanoparticle, right? And in this way, if all the nanoparticles are being coated with, or they have the surface absorbed polymer, so then the steric hindrances or configurational constraints will not allow the nanoparticle fusion. Now the question comes that how this shell, which is created by the polymer or by the surfactant, can help us to generate a stable colloidal solution. Now we are coming to another story. That is over here. You know the potential energy diagram? Everybody, when we start with the physical chemistry, thermodynamics, we always start with the potential energy diagram, right? So here we say that the potential energy is on the y-axis, and here we say that it is the distance among the interacting species. Suppose if we talk about the hydrogen molecule formation, suppose if somebody asks you that how the hydrogen molecule formation is occurring among the hydrogen atoms, you can say the best way to explain that, rather than any kind of synthetic process, you will be saying that it is the potential energy diagram. So this is the potential energy when it is zero, right? When the two hydrogen atoms are infinitely apart from one another. This hydrogen atom has no sense of the presence of another hydrogen atom. So therefore, the potential energy of interaction between the two atoms, two hydrogen atoms, is nil. So therefore, the potential energy means they have no sense that another hydrogen atom is present in the vicinity. But when they start coming closer to one another, the potential energy starts decreasing like this, right? Now the question is, you might be asking, what compels the potential energy to fall? The reason for that is the hydrogen atom has one proton, right? So, and there is the electron density of one electron. Likewise, the same is the story over here. So what is happening? The electron density of one hydrogen atom that interacts with the nucleus of another one, and likewise the electron density of another hydrogen atom interacts with the nucleus of the other. So that brings the one hydrogen atom closer to another one, and hence because their energy stabilizes, because the potential energy attraction set in, and therefore the potential energy of the system falls, and that is why the potential energy keeps on decreasing. And at this point, potential energy starts increasing instantaneously. What is this point? Where the hydrogen covalent bond is established. This is the point where the maximum electrostatic interactions are established between the electron cloud of one atom with the nucleus and vice versa. Now what happens beyond that? We are decreasing the distance. This distance is decreasing. It means that I am saying that this is the distance that keeps you minimum potential energy. Now, but what happens beyond that? When we further decrease the distance, then this nucleus starts sensing the presence of another nucleus. You got my point? And then the repulsive interactions set in. As soon as the repulsive interactions set in, the system gets destabilized and potential energy instantaneously increases. Now, what is the meaning of this whole story? The meaning of this potential energy diagram is we are going to apply on the colloidal stability. I mean to say that I have produced one, you might consider a hydrogen atom, a particle as a hydrogen atom, and there is another one, right? So I want this particle must be away from the other particle. There must not be any kind of attractive interaction between the two particles. That is the colloidal stabilization. That is required for any kind of application in nanotechnology. You cannot use the nanoparticle for any application unless they are completely separately swimming in the water domain. You got my point? So without independent existence of the particle, you cannot use them for any kind of application. I'll explain that when I come to the application part. So you have to create the reaction conditions, solution condition in such a manner that this particle should not merge with another particle like this, right? So therefore, we need not this kind of potential energy dip when the colloidal particles are interacting, but we need this place. We should have the much higher potential energy. So here is the potential energy of the interacting particle. It's the same diagram you see over here. This is given by DLVO theory, so it's a very common theory. And the concluding part of this theory is V is not the volume, it's the interacting potential, total interacting potential. It's a theoretical concept. It's the combination of the electrostatic contribution and the non-electrostatic contribution. That is the contribution that is provided by the double layer, electrical double layer. So I'm talking about the electrical double layer that is being created by the colloidal surfactant molecules, and then the non-electrical, that's water-wall interaction. You already know what is the definition of the water-wall interaction. So those interactions actually occurring between the non-polar entities. So here you see that if I choose the same way as the way I have explained over here, the two particles are interacting. If the two particles are going to merge, nanoparticles are going to merge, then you won't be having a solution like this. You cannot have a solution like this. Then as soon as you are going to prepare the gold nanoparticle solution, within 5-10 minutes or half an hour, all gold nanoparticles are settled because of the aggregation among the particles, right? And that is not a colloidal solution. And you cannot use them for any kind of application. But if you have to use them in any kind of application, you must have a stable solution. So the stable solution you can have only if there are repulsive interaction, not the attractive, but the repulsive interaction. So it means that this is the attractive interaction. The attractive interaction are because of the water wall interaction. Now, there is another confusing thing here. If somebody asks you that, okay, I understand the nanoparticle in the solution. So here I have a solution of the nanoparticle. Here I have one particle. I have another particle. Should this nanoparticle interact with this nanoparticle through the polar interaction or the non-polar interaction? I'll be saying that there are two contributions of the interactions, a polar and the non-polar. Then somebody can ask you, what is the origin of the polar interaction? Why this particle is going to interact with this one? No, first I should explain the non-polar interaction. Why this particle is going to interact with this through the water wall interaction, that is the non-polar interaction. Now, here is a problem. If somebody asks you, why we are standing on the surface of the planet, why can't we fly away? Then what should be the answer? Because of?
Gravitational force.
Gravitational force. Do you know the origin of the gravitational force? You know the origin of the magnetic field on the surface of the planet, right? You know the origin of the electric field. Because of that, we have the glowing of the bulb and the tube, right? Do you have any information what causes the gravitational force? It is always the matter attracts the matter, right? So we still don't have a clear explanation why matter attracts the matter. That is because our modern science is still silent about that. We know the gravity is there because of the internal structure of the planet. Every planet has a gravitational pull that is proportional to the magnitude of the size of the planet, right? But we still do not know why matter attracts matter. The same definition applies over here. It means that we will say the matter attracts matter. Whenever they say matter attracts matter, then we will say it is the non-polar interactions are in action, right? When we have to say the electrostatic interaction, we have to prove that the positive electrostatic potential is going to interact with the negative electrostatic potential. Only then we can say that this is because of the electrostatic interaction. But here that is not the case. We cannot say that this is electropositive, this is electronegative. That is not the case, because both are of the same crystal, same atomic arrangement, same surface chemistry. So therefore that term cannot be applied over here. So therefore it is predominantly the non-polar interaction, and we have to. This is what over here. The non-polar interaction, you see, the VA is a van der Waals interaction. If the van der Waals interaction apply, if they are in action, so then there is fall in the potential energy, and eventually the particles are going to merge, and it is not a stable reliable solution. It means that the polar, now how the polar interactions are going to work? We are in fact producing the electric double layer over here. The charge on the surface is, if you are using catalytic surfactant, the charge on the surface is partial positive delta, it's a smaller delta referring to the electrostatic potential, and the same charge is over here. When the same charge entities come close to each other, they start repelling one another. They are not going to attract. That is the stabilization. So this is the colloidal stabilization. So you have to say that in order to, this is a very important concept. You cannot have the stabilization without creating the charge on the surface of the nanoparticle, and the charge on the surface of the nanoparticle has to be created either by choosing the surface active molecule or by choosing a specific kind of a polymer that can produce the stability. That is the meaning of the stability of the colloids. So now there is another slightly confusing concept which is there is another slightly confusing concept. What is that? You might have heard several times who are working in gold nanoparticle synthesis. Sometimes you see that when you synthesized gold and nanoparticle, and if I'm not dealing with any kind of electrostatic or non-electrostatic interactions among the particle, but still the particles are going to settle down. It means that we are ignoring the gravity, but you cannot ignore the gravity. Gravitational pull is if the gravitational pull is the matter attracts to matter, this attractive interactions are working among the particle, right? And then how can we ignore the attractive interaction applying between the nanoparticle and the earth, right? So earth and we are here because of the matter attracts to matter. So the same philosophy we are going to apply it over here. For example, I have a water solution, right? And now in this water solution, I have a stable colloids, gold and nanoparticle. The first question is, are they under the effect of gravity or not? Yes, absolutely. Every form of matter is under the effect of gravity, no matter how tiny, no matter how big that is. But the question is, when we have produced a stable colloid, as I explained in the previous slide, when we produce the stable colloids, then if we say that okay, the colloid is stable for several months, where is the gravitational pull? Now, should the gravity is working or not? How can you say that the gravity is not working on the solid particle? They are suspended in the solution, right? No, gravity is working. But then if the gravity is working, and then what is the opposing force to the gravity? You got my point? It means that gravity is still working. But the question is, which force allows the particle to keep swimming, suspended, and not responding to the gravity? Or that force is predominantly stronger than the gravitational pull? That is over here. Okay, so in order to go through, it's a slightly complicated, but it's a very clear mathematical treatment. So here is the particle. This particle the settlement of the particle under the gravitational pull is known as the displacement with respect to time, and this is the concluding equation. So I'm coming over here and I'll explain what's the meaning of this. The first thing is that the gravitational force is mass of the object multiplied by the gravity. The G is the gravitational pull, not the gravitational constant. It's the gravity and the gravitational constant. Both are the separate terms. So mass can be volume multiplied by the density of the particle, and this is the gravitational pull, right? And there is another force which is applying on the suspended particle, that is the buoyancy. So what is that? It is the mass of the water molecule and multiplied by the gravity. So again, mass can be the volume and the density of water. The third is the frictional force. What is that? Frictional drag. When the particle is going to suspend, I'm going to say when the particle is going to settle under the effect of gravity, it is experiencing the frictional drag. So the three forces are going to apply when the particle is going to settle on the bottom. The first one, the force due to gravity. Second one, buoyancy, and the third one, it is the gravity. The third one is the friction. And the frictional force, you see that it is the viscous drag. That is the frictional coefficient. So it's 6 pi eta is the viscosity, r is the radius of the particle, dx over dt. Now, if you take all the three equations and all the three components equal to 0, if you have to keep the particle suspended, right? Now you see that this is negative and this is negative. The reason is the gravitational force is pulling, but these two forces, they are working against the pull. Buoyancy wants to keep the particle suspended, and then the friction again wants to keep the particle suspended, and it's opposing to that of the gravity. That is why you have the negative sign. If you plug the values for all of them, eventually you come to this equation. This is the rate of the settlement of the particle under the effect of gravitational pull, and you see over here, density of the particle minus density of the water. Greater the density difference, greater is the displacement under the effect of the gravitational pull. Greater the radius, greater is the displacement under the gravitational pull. But what is opposing? Opposing, you see the viscous drag. If the viscous drag, it means that if the medium is more viscous, right, so it will oppose the settlement of the particle at the bottom. But where is the viscous drag? Viscosity of the water is constant. Viscosity of the water is constant. We know what is the viscosity. But how the viscous drag can be imposed, that is what here I have explained. The viscous drag, where we talk about the electrical double layer. The stronger the electrical double layer or the surfactant which we are going to use, the stronger are the electrostatic interaction with the water molecule, and that is enhancing the viscous drag or the frictional forces, and they are opposing the settlement of the particle. It means that if you have to prepare the stable colloidal solution, you have to be very careful that you have to enhance the frictional drag and the viscosity of the medium by putting an effective electrical double layer, and that will allow the nanoparticle to keep floating in the solution, and that is a stable colloidal solution. Everybody understands? Any question? Okay, I'll take another 5 to 7 minutes, so I'll try to conclude it. Okay, now there is another aspect. If we have to use the nanoparticle for a typical kind of a device, we have to control the shape of the nanoparticle. For example, if somebody asks you, okay, I have very small cell phone or any other instrument, and I have very tiny parts of that device. So that tiny parts of the device are composed of nanomaterial of specific shape and size. Among them, the wires are very important. Ribbons of the wires are very, very important in order to put them in the form of small parts of our device. How they can be synthesized? Chemistry. So we, as I told you that when we use the sodium borohydride to produce the atoms instantaneously nucleate into the nucleating entities. So this is a nucleating center, in fact, where certain number of atoms are going to aggregate, maybe 100, 200, 600, something like that. So it's a small crystal, very tiny crystal, and it has a specific planes. So if you look at the inorganic chemistry and you talk about the crystal structure, so you know that for any crystal, so there are 3 kinds of crystal plane: 100, 110, and 111, according to the 3 dimensions in which direction the crystal grows. Right. So on the basis of that, you have 3 crystal planes. By manipulating, by passivating, by blocking certain crystal planes, suppose if I want to grow this nucleating center into a ribbon or a wire, I have to block the other crystal planes and only allow the growth to be happened over here. So you see that the crystal plane, this one, it's 001 and 001. You can see over here all 111. So they are being blocked. And only this crystal plane, so that is 110, and only the nucleation is happening on this one, blocked by placing the surfactant molecules and allow the crystallization to happen like this. So this is I mean to say, suppose if you ask me in a very simple language that how can we do it, I say that it is the research and the experience when you will keep on going through or synthesizing the nanoparticle and slowly manipulating with the surfactant. Eventually you will come to know that how you can produce the spherical nanoparticle, how you can produce the hexagonal nanoparticle, how you can produce the rod-shaped nanoparticle or the wire-shaped ribbon shape. So in this way you can produce the wire-shaped nanoparticle, and here they are. How? And this what we developed. You see, these are the transmission electron microscope where we use the same kind of methodology. It's a seed growth method. Initially we produce a very tiny crystals of gold nanoparticles, spherical shape, all spherical shape. We reuse them in the second step to produce a rod-like nanoparticle, and we again continue with the synthesis by manipulating with the concentration of the surfactant, by blocking the crystal planes, and eventually we'll come to the nanoribbons or nanowires. And I think in next few lectures I'll explain that from in which devices or in which applications you will be using the nanowires. Okay, then apart from this, you should have, it's not only the wire, but sometimes self-assembled nanoparticles, so they are also required. Right? Again, I am using a different kind of surfactant. So here, these are biologically active surfactants. These are the lipids, phospholipid molecules. They are also surface active molecules, but they are much more hydrophobic, non-polar in comparison to the conventional surfactant. So I mean to say that you have to manipulate with a different kind of a molecule so that you have the nanoparticle arranged in chains like this, right? And it's a one-dimensional structure. If you do not want to have the nanowire, because the nanowire is a crystalline which runs from one side to another side, but this is the one-dimensional assembly of the nanoparticle. Suppose if you ask me what is the meaning for this, it acts as a sensor. When the nanoparticles are separately dispersed, I mean to say over here, it has a different way it absorbs, it interacts with the electromagnetic current. But when the nanoparticles in one-dimensional or in aggregated state, so then it has a different way of interacting with the wavefront or electromagnetic radiation. So that will be a kind of a sensing technique to apply for some kind of a technique. So, okay. Actually, I forgot that why I added this micelle formation, but I'll explain it in the next lecture, that how the micelles are formed. Okay, self-assemblies can also be achieved by using polymers. Here it is the block polymer, right? So, and then here you have the redox chemistry in action. I'll say you have to choose a polymer which can be used for the redox reaction. I mean, here you have the ether oxygens, so they can supply the electrons to the gold ion, and in this way it can convert into the gold nanoparticle. In fact, this reaction is happening in the micelles. It's a polymeric micelle. It's a micelle of a polymer. So let me just in one minute, I should explain you what is the meaning of this. It's a polyethylene oxide, polypropylene oxide, and polyethylene oxide. It's a very common polymer which is frequently used in all cosmetics. So what happens when it aggregates? it aggregates in the form of this structure, right? So this part is the PPO, polypropylene oxide. This side is PEO and PEO. You see a cavity formation, and this cavity in fact triggers a reduction reaction. So I mean to say, when the gold ions, so they come in this cavity, they get reduced by adding 3 electrons, and the gold atom is produced, right? So the kind of a reaction was shown over there. The gold nanoparticles are produced then in the cavity. So it means that in the cavity you have the gold nanoparticle, because you have created the atoms in the cavity, so you will create the gold nanoparticle. But how do you know that this reaction has happened? How do you know this reaction actually occurs? So then again I'll say the microscopic imaging. You see the micelles? The micelles are only the spheres, but the dark dots, you see the dark dots? They are the gold nanoparticle which I have shown over here. So they are over here. So all dark dots, so they are, you see in the scanning electron microscope, where you could see clearly the gold nanoparticle. You can prove them by what we call EDS analysis. So it is, it's a scanning analysis where we allow the high intensity radiations and ejection of the valence electron take place. With the help of that, we can prove that the electrons which are being ejected, they are indeed ejected from the gold atoms or the gold nanoparticles. So that is the way to prove this. So I need to say that there are different ways to produce the self-assemblies or a specific shape. So coming back again to just remind you that we first talk about the stabilization of the gold nanoparticle, then we talk about producing the nanomers or the nano ribbon, and then we talk about producing one-dimensional self-assembled structures like this, and then we talk about the self-assembled structure where we could have the growth of the nanoparticle in the micelles. So all these structures, so they have the applications which we will talk about after some time. I'm not going to explain all the application, but I'll take just few examples. Okay, so now actually, yeah, I am just last slide. And this is very important. Suppose if somebody asks you that what is the best way for a student in a college where there is no instrumentation available to see that if the what kind of gold nanoparticle of specific shape we have produced, then the UV visible spectroscopy that is available everywhere. I think now this instrument is available in high schools as well, right? So we can simply use that instrument to, for the time being, we can check if the gold nanoparticles are produced and which kind of dimension we are expecting. Qualitatively, we can on the shape of the UV absorbance, we can just at least we can have some idea that what kind of the shape of the particle is. So you see over here the UV spectrum, so slightly that is complicated, so I'm going to explain it in 1 minute. So this is the UV spectrum, absorbance and the wavelength in nanometer, right? So for a red color gold nanoparticle suspension, the one which I showed in the first few slides, so you should have the absorbance something like this, and this should be close to 520 nanometer. If you have the absorbance of that solution, red color solution, close to this, it means that you are having somewhere polyhedral nanoparticle, dimensions from anywhere 5 to 200 nanometer, right? If this absorbance gets broader, the peak gets broader, it means the shape changes from sphere to some other like triangle or some plate-like or a bigger molecule of a different dimension. That is, if the peak is going to be a broader peak or slightly shifted, blue shifted, red shifted. But if you have the absorbance like this, wavelength nanometer, if you have absorbance at much red shifted, instead of here it was 520 nanometer, right, and this is more than 650 nanometer, it means you have only rods. It is very hard to get the rods, only rods. Usually the solution contains a smaller amount of the spherical particle. It means that you will have a smaller peak over here, sorry, just a minute. So you have a smaller peak over here, right, and for the spherical particles, right, at 520 nanometer, and a larger peak over here, and that's what we do. So if you have only this peak close to 520, it means you have only polyhedral particles. But if you have double peak, the one is over here, another one is over here, it means that you have rods as well as the polyhedral particle. But if this peak is shifted more and more, red shifted, it means that the size of the rod increases. You see, when it is close to 700, the size is this. When it is close to 820, the size increases, length increases, sorry about that. The length correctly is known as the aspect ratio. The aspect ratio increases, right? And here you see that if it's further shifted to red, close to the near IR, right? So the length further increases. So I mean to say, this is the simple way you can test what kind of nanoparticles you have synthesized and what should be the tentative shape. If it is only one kind of shape, you should have only one kind of absorbance. If you have the mixture of different particles, you have the different shapes. But this particular peak will only appear if you have the rods. If your solution is not containing the rod, this peak will not appear, right? So in this way you can just test your gold nanoparticle synthesis, and eventually nanotechnology is scientific modern times with significant implication in all walks of life. Implication, I am taking it slightly in a negative sense, toxicity, but I have not yet explained the toxicity. We will be talking about when we'll be explaining the bioapplicability. Prevention is the best healthcare. Nanoscopic detection is the key to the prevention. Sorry, I should have included some more conclusion that how we can stabilize the nanoparticle and what are the characteristic feature for the stabilization. So you may consider that as well. So anyway, so we conclude this, and yeah, we are slightly 10 minutes above our the normal lecture time, but you are most welcome to ask me a question. Thank you so much for your attention. Go ahead, please. Go ahead. Don't hesitate.
Could you throw some light on the core cell synthesis? In the micellar synthesis of nanoparticles.
Yeah, that will be in the that is coming, I think.
You can control the particle size.
Exactly. Yeah. So that when I'll be explaining first the micellar system, means the surfactant and surfactant property, how the micelles are formed, how the micelles are going to change shape, and how that shape is going to alter the dimensions of the network. Yes, please.
Sir, as you said that we may use fatty acid as a substitute, so we may use amino acid which have a polar and non-polar both sides.
Amino acids are zwitterionic molecules, right? So zwitterionic molecules are usually not surface active, they are not amphiphilic unless you are going to add a known polar functional group. So there are zwitterionic surfactants. So it means that you will be using derivatives of amino acids which are surface active. It means the amino acids which you are talking about, the 20 amino acids, probably they are not good. Some people use some of the amino acids. You may predominantly non-polar amino acids can be used, but they are not going to produce a very stable colloidal system. They can be used, means I mean to say when you look through the paper published, you will see the amino acids can be divided into polar, non-polar categories. So non-polar amino acids, predominantly non-polar, all of them are water soluble most of the time, so you have to use that. Okay, thank you so much. See you in the next session.
Thank you, sir, for such informative lecture. Now, our next tutorial will be at 1:30 at Department of